Hello students. So today's topic is group 16 elements. So let's see group 16 elements. What are they? That is oxygen, sulfur, selenium, TPO. So general electronic configuration of the outermost orbital will be ns2np4. Physical properties is EGE. So as you can see, there is a exception, that is the electron gain enthalpy always decreases down the group, but here as you can see that the oxygen has the least electron gain enthalpy in this group, and the rest of the thing or rest of the elements present in this group are having the same trend, that is electron gain enthalpy decreases down the group, but the exception is our oxygen, that is it has least electron gain enthalpy in this group. Now, in ionization enthalpy with no exception, that is decreases down the group. Atomic radii also with no exception increases down the group. Then our chemical properties, oxidation state is -2, reactivity towards hydrogen. Okay, so here we can see some special traits. Okay, where they are forming the compounds like H2S, H2SC. Okay, so let's see what are the special traits. First is our acidic character. Now acidic character increases down the group. That means H2T greater than H2SC greater than H2S greater than our H2O. Then our thermal stability. Now thermal stability, the order get reserved. In the case of thermal stability, the order gets reversed. That means thermal stability decreases down the group. That means H2O greater than H2S greater than H2SC greater than H2T. Now reducing character is follows the same order as the our acidic character. That means H2O is less than H2S, less than H2SC, less than our H2T. Now there is a same trend in the melting point and boiling point of this hydrides, but what we are going to see that there is a exceptional order, that is H2O greater than H2T greater than H2AC greater than our H2S. That means H2O, in if we follow this order, then H2 is have to be the least, but here we can see H2 is have the highest boiling and melting point here because of its hydrogen bond. Okay, it forms a chain like structure, so that's why it has the highest boiling point and melting point, so that's why it is highest in this group. Next is reactivity towards oxygen, that it forms E2, EO2 and EO3. So we know its example, that is SO2, SO3, right? Like that forms the hydrides. Next is the reactivity towards halogen. So it forms three kinds of compound, as you can see. First is E2X2, X6 and EX4. So let us discuss what is E. E is ACTPO. Next our halides, it is FCl, Bri. Now in SF6 we already know how its structure is, right? That is square bipyramidal. Okay, it is elaborately discussed in our hybridization videos. Please see it if you haven't seen it. Link is given in the description. So this because of this kind of structure, it has a considerable amount of steric hindrance. So that's why it is not highly reactive. That means it is what we can say unreactive or non-reactive because of this steric hindrance. Next comes our SF4. Its structure is like seesaw. Okay, so how it is structured, let us see that. Okay, so this kind of seesaw-like structure. Okay, but now there is also a special trait in this EF4 or EX4 molecule, that is this SF4 is our gas, but this ACF4 is our liquid, and this TF4 is our solid. Okay, next fourth is AC2S2Cl2 S2Br2. So they are diameric and goes into our disproportionation reaction. So please remember it, disproportionation reaction. Next is dioxygen. So dioxygen is very important, right? Because we can live without it. So its preparation reaction, we have all read it from our childhood. That is 2KClO3. If we heat it, it gives us, in presence of MnO2, it gives us 2KCl plus 3O2. Now oxides. Now there are several oxides, and they have different nature. So let us first describe the acetic oxides. So acidic oxides are mostly non-metal oxide. That is SO2, Cl2O7, N2O5. But here also is exception. So what are the exceptions? They are V2O5, CrO3, Mn2O7. Next is basic oxides. They are metal oxides, that is Na2O, CaO, BaO. Okay. Then comes our amphoteric oxide, that is our Al2O3. Then our neutral oxide, that is CONO N2OH2. Now this neutral oxide is very, very important, okay, because it is often asked in it, then to point out the neutral oxide. So they will be CONO N2O and H2. So then comes our mixed oxide. It is also very, very important, okay. So what are they? That is Pb3O4, MgAl2O4 and Fe3O4. Next is our ozone or O3. So preparation reaction, silent electrical discharge. Then it gives us from 3O2, gives us 2O3. Important reactions of ozone, that is if O3 is reacted with Ag metal, then it gives us Ag2O. Now its oxidation property is shown here, that is Fe2 plus, it gives us Fe3 plus, and if it is reacted with I2, then it forms the respective acid HiO3. If it is reacted with phosphorus, it gives us a respective acid, that is H3PO4, and it is reacted with sulfur, it gives us also the respective acid, that is our H2SO4. Next is our special reaction, that is O3. If it is reacted with Hg, it gives us Hg2O. Why it is special? Because this is called tailing, okay, tailing or test of O3. So please remember this reaction very carefully. Then comes our resonance. Now, as we can see that this ozone has one double bond. So this double bond gets resonated and it can move like this. Okay, so this is the resonating structure. And also when this kind of compounds like O3, which have one double bond and it also takes part in resonance, it forms delocalized pi electrons. Okay, so it also come in question that in which of the compounds there is delocalized pi electrons. So if you find a compound like this which have a double bond and also takes part in resonance, so they will have delocalized pi electrons. Next is our sulfur. Now we are discussing allotropes of sulfur. So there are two allotropes, that is monoclinic sulfur and rhombic sulfur. Now monoclinic sulfur is stable above 369 Kelvin and rhombic sulfur is stable below 369 Kelvin. But these two kinds of sulfur are stable at only 369 Kelvin. So this temperature is called transition temperature. Okay. Next is our sulfur dioxide, SO2. Its preparation reaction is shown here. SO3 2 minus plus 2H plus gives us H2O plus SO2. Next is reactions. Reactions are 2NaOH plus SO2 gives us Na2SO3 plus H2O. SO2 plus Cl2 gives us SO2Cl2, and next is our 2SO2 plus O2. B2O5 is catalyst, gives us 2SO3. It is also called contact process. We are going to read it in preparation of sulfuric acid, so it is also a very important reaction here. Next is our SO2 plus H2O gives us H2SO3. Now let us see the structure of the SO2. It is also like the structure of our O3, and it has also a double bond and takes part in resonance, so it will also have delocalized pi electrons. Next is our oxo acids of sulfur. As you can see, first acid is our H2SO3, sulfurous acid. So as you can see that here it has a lone pair on the upper side of it, and one side is OH and double bond O. Now in the next acid we can see where it is H2SO4, the lone pair is replaced with the double bond O, and the rest of these are the same. Next is our pyrosulfuric acid. Pyrosulfuric acid is, as you can see, that one of the this OH of the sulfuric acid is gets dehydrated and forms a bridging oxygen, so it is then it is forming our pyrosulfuric acid, that is H2S2O7. Okay. Next is our peroxo disulfuric acid. So here as you can see that it is not a bridging oxygen, but two bridging oxygen are present. So this is a characteristic structure, that is H2S2O8. Now this H2S2O7 is also called oleum, and this H2S2O7 is called Marshall's acid. Okay. Now let us see another important structure, that is our H2SO5. So just remember the structure, because only the structure sometimes they ask you from questions from these structures. That is one side is OH, one side, and the two side is double bond, and but here is the characteristic, that is OOH. So this is the structure of H2SO5. Next is sulfuric acid. Now process of preparation, as I have said there, that is first process is 2SO2 plus O2, B2O5 catalyst, 720 Kelvin temperature, 5 bar pressure, and it gives us 2SO3. So it is called contact process. Next is SO3 plus H2SO4 gives us H2S2O7, or I have said it, oleum. Next is H2S2O7 is diluted in water, and it gives us the desired concentration of H2SO4, that is nearly 99%. Okay. Next is our physical properties, that is it is added to the water slowly and not by adding the water to acid. So what does this point mean? That is we can add sulfuric acid to water slowly by stirring it, but not adding water to sulfuric acid. If we do this, that adding water to sulfuric acid is very dangerous, because acidic fumes generated, so it can just burn your face and everything. So it is never done, that is water to acid, but acid to water is done. Okay. Then it is also highly dense, that's why sulfuric acid is called oil of vitriol. Next is chemical properties. Acidic nature, we know sulfuric acid is a very strong acid, so let us see its acidic nature, that is H2SO4 in water gives us H plus plus HSO4 minus, and HSO4 minus in water also gives us H plus per SO4 2 minus. Dehydrating agent, now this sulfuric acid also acts as dehydrating agent, that is C12H12O C12H22O11 gives us concentrated H2SO4 and gives us 12C, or what we can say, dehydrated carbon, and 11H2. Also oxalic acid is dehydrated in this case, it is CO plus CO2 plus H2O. Next is some important reactions of sulfuric acid, that is NaNO3 plus H2SO4, that is NaHSO4 plus HNO3. This is the preparation reaction for our nitric acid. Next is NaCl plus H2SO4, it gives us NaHSO4 plus HCl, it is preparation reaction for our hydrochloric acid. Next is oxidizing agent, that is H2SO4 gives us H2O, SO2, and this nascent oxygen. So that's why it takes part in the oxidizing reaction, so it is a oxidizing agent. Next is BaCl2 plus H2SO4. It gives us BaSO4 plus 2HCl. Now this is the identification test for H2SO4. Okay, so if we, in a solution, if we, in presence of H2SO4, if we add BaCl2, the form it, the colorless solution, it becomes white. So that indicates the presence of H2SO4. So it is a identification reaction. Okay. Next is decomposition. Decomposition is H2SO4 is decomposed into SO3 and H2. Okay. So this is it for our group 16 elements.